Okay, so what I'm about to show you is critically important because it's about the big picture. It's about tying together everything that we've been doing, okay? It's about tying together everything we've been doing. And so I want to just use that oil example that you worked on. We worked on last Thursday and you worked on in homework. So here are these two graphs. On the left graph, you see on the y-axis meters cubed per day, and on the x-axis days. And on the right graph, you see meters cubed on the y-axis and days. So just take a moment to explain what each of these functions are. So just get a partner, explain exactly what each of these functions show. What is the left function? What is it tracking or tracing, or what is it? What information does it reveal? And what does the right function, what does that function reveal? So talk to the person next to you, take about a minute. Go. Derivative, what's that? Derivative, what's that? Yeah, we would never mention that word. Rate of change function. Rate of change function. Okay. So the left graph, you should have talked about something like this. This is the rate of change of oil entering the ocean at any number of days after the leak begins. So given any number of days that have gone by, that red curve will then tell you the corresponding rate of change of oil entering the ocean at that number of days. Okay? And what does the right graph show? Does it show the rate of change? No. Y values on that graph tell you what? Quantity, right? So we talked about accumulation, we talked about amount. So you could say it's the accumulated volume of oil leaked at any number of days after the leak begins. Okay? So it's showing the accumulation of volume of oil leaked into the ocean. Okay. So we've talked about the calculus is all about one of two endeavors. You know how much you have, you know how much of something you have, and you want to know how fast it's changing, or you know how fast something is changing, and you want to know how much of it you have. Okay? So we are on journey number 2. You know how fast something is changing. In other words, we're given a rate of change function, and we want to know how much of it we have. So the types of problems that we're trying to solve at this point will be, we know what the rate of change is for some quantity, and we want to know the accumulation of that amount, or we want to get a total amount. Okay? So given what's on the left, we want to know what's on the right. So what is the key to that? So what is going to be our key? So we've got rate of change, and we want accumulated amount. What makes this difficult is that rate is continually changing. That rate is continually changing. Okay? So our key to doing this is going to be constant rate of change. So the key to developing function v from function r sub v is going to be constant rate of change. Okay? And that's what we've been working on the last month. We've been working really hard on constant rate of change because those are all the tools, all those are the tools that are going to allow us to develop the blue function from the red function. So let's see that. So if I had a constant rate, m, in meters cubed per day, what does that mean, or what do I know? I've got some constant rate in meters cubed per day. What could I conclude? What does a constant rate of change mean? In this case, a meter cubed per day. Okay? The volume of the oil leak changing over time. Okay, but specifically, what does that value m mean? We've worked hard on this. Okay, I believe that you know. So I want you guys to see if you can tell the person next to you what does it mean if you have the value of m, the constant rate of change of meters cubed per day? What's the broad meaning? Remember, we talked about this. What's the broad meaning of that constant rate? Go. I want to get the back cans bright. I can't do that.
I don't. This class is having problems, and we actually don't deal with the lights.
Okay.
And the electricians are coming in tomorrow morning to fix it.
Because sometimes I
but
come in and it's like that. Someone's able to do it.
I don't know what's going on.
Okay.
Like even so, my supervisor actually drew out like the light switches here, like how each of them work. So we can try these out. You said you want the back ones bright.
So the front ones are nice and bright,
Right.
but I can't get the back ones bright and have these off. Those off the way I have them.
Oh no. All right.
Okay, do you want to give it a shot now? You had your hand raised. Tell me.
Yeah, the change in the volume
Uh-huh.
is equal to the rate of change times the change in the date.
Good. All right. So, given any change in number of days, what can we conclude? Given any change in number of days, we can conclude that change in volume is m times that change in the number of days. Okay? So, it's got to start sticking at some point. It's been 3 weeks or a month that we've been working on that. Okay? That given any change in time, the change in volume is m times the change in time. But what is the change in volume? The change in volume is that's a little bit of accumulation, you see? So given m, given a rate of change, this principle right here calculates a little bit of change, accumulation. See, that's taking us from rate of change to accumulation. And then, from there, we could calculate some final volume. How can we calculate some final volume now? So we've got a change in volume. You add it to? Yeah, so and then any change in volume, a final volume would be any initial amount of volume times the change. And that change is our m times dt. So this is another principle we worked hard on. But so these principles of constant rate of change, these are the keys to, you know the rate of change, you know how fast it's changing, and you want to know how much you have. Because m is, given a constant rate, given a constant rate, what does dv equals m dt tell you? It gives you a little bit of accumulation. And then also, it gives you a total accumulation or a total amount. It's okay if you can't get it.
Yeah, I know. The electrician's coming tomorrow.
Okay, all right. Thanks.
Because even other instructors are.
Okay, thank you very much. So do you see how all this stuff that we've been doing, constant rate of change, this dv equals mdt, v final equals v initial plus dv, is the key to, if you know the constant rate, you can get a little bit of accumulation, and you can get a final amount, or a total amount of accumulation. So these are our tools that will allow us to develop an accumulation or an amount function from a rate of change function. So does this help to kind of tie a lot of things together? So this is the big picture that you always have to have in mind. This is the big picture you always have to have in mind when we're getting into the minutia of doing calculations and working on details that are kind of maybe feel like they're on the periphery. You still have to tie them into this is what we're doing here now in the next couple weeks. Anybody have a question? How are we doing on internet? How many people still don't have internet? It's better. It's still not good enough. All right. Well, we'll just keep progressing here. So let this sink in. Go back to the video. Watch this part again. This is the big picture. And like I said, everything that we do, you have to have this big picture in mind. Okay, so in your homework, you looked at this rate function, and I asked you to highlight points on the rate function. Was it every 0.3? Was it every 0.3 days? Is that right? So you were to highlight points every 0.3 days. So the first one was at 0, is that right? So that gave you this point right here. Maybe. And then at 0.3, we highlight this point. Did I just add a point to the graph? No, it was already there. I'm just highlighting it, right? That whole red curve is all points, right? It's all points. 0.9. Was 1.2 the last one?
Yes.
Okay. And then I asked you to what did I do? Then I asked you to write the coordinates exactly, right? I write the coordinates of each point exactly. So let's just do one of those. So maybe let's do this one right here. So what are the coordinates of that point? The exact coordinates. What's the x coordinate exactly? 0.6. I'm zoomed in, so the pen doesn't work good. All right, 0.6. Okay, and so to represent this y coordinate exactly, it would be r sub v of 0.6, right? R. Okay, is there a question? Anybody have a question? Okay. And what does that mean? So what does this right there, does anybody have a question? What does that mean right there? R sub v of 0.6. What's that? He says the rate of change at 0.6 days. It's the rate of change at 0.6 days, right? A rate of change function, values of the dependent variable, okay? Give values of rate of change, right? Give values of rate of change, the dependent variable, okay? And so then I asked you to estimate that, right? Estimate that. What would you estimate that value to be? So this is the rate of change at 0.6 days, and now I want to estimate that. What would you estimate it to be? She's saying somewhere around 12 meters cubed per day. What do you think? Yeah, exactly. You're going to look at maybe just a little bit less than 12. Each of these is like, yeah, like 12. It's good. Okay, so what would the graph look like? What would it look like if we had a constant rate of that, whatever that rate is, a constant rate for the next 0.3, so for this interval right here, and actually this is where, when we break up intervals like this is going to be a moment. Is that a big moment or a small moment? It's a big moment, right? This is a large moment, 0.3 days. Okay? And we're going to call this moments we're going to use delta. Delta t. So what is dt again? dt is a little change. Okay? A moment is any size interval. Okay? And so now I'm going to use the intervals that you did for your homework, call it a moment, and that's going to be delta t. Okay? So I have this delta t moment. It starts at 0.6. It ends at 0.9. What would a new rate of change function look like for that 0.3 days that had a constant rate of change of this value, RV of 0.6? Could you draw it in your notes? Okay. what would it look like if I drew a new rate of change function that was a constant rate for this whole moment of R of V of 0.6? Can you draw it in your notes? Go. That's a fair question, right? That's a good question. Okay. I thought you were looking like, okay. Okay, so I'm guessing there are two in the world out there. There are two possible answers: a straight line from this black point to this black point, or a horizontal line from this black point across. So, which shows the constant rate of RV of 0.6 in that moment? Is it the exhibit A, a diagonal line from black point to black point, or the horizontal line starting at the black point? A or B? Good, good, okay. This is it. That's what I described. A constant rate of change for that whole moment of RV of 0.6. Why do we want that? Why do we want that? We talked about it earlier. Having a constant rate is going to enable us to use the math of constant rate of change to build accumulation and amount. We can use, now that we've got this constant rate, now we have an interval for which we can say dV equals m dt. And we can say the final value of V is the initial value of V plus dV. Okay? We can't do that with the red curve because as soon as a little time goes by, the rate is different. But with this constant rate here, we can apply all those tools we've learned over the last month. You see? Okay, so I want to do this for every moment. I want to show in every moment, I want to show a constant rate of change equal to the rate at the beginning of the moment. So we want to create a constant rate of change in every moment such that that constant rate is equal to the actual rate at the beginning of every moment. Can you do it? Go. Can you do it? What's that? So, what I ask you to do is now repeat what we did for this moment for all the moments. Repeat what we did for this moment for 0.6 to 0.9 for every single moment. And so then in each individual moment, you're going to create a constant rate of change that's equal to the actual rate of change at the beginning of the moment. Is that better? So you've got 1, 2. So I want to see how we're doing. Okay, in the first moment, what is the rate at the start? What's exactly what is the rate at the start of that moment? Exactly. What's the rate at the start of the first moment? Exactly. RV of 0. And it's about 29, 28. Right. Okay? So what would it mean to represent a constant rate of that amount for that first moment? Horizontal line at that value. And what is that value exactly? What is that constant rate exactly? RV of 0. Where do we get that? Where do we see that value, like as an estimate? The y-axis is telling us what that is. It's about 28 or 29 meters cubed per day. Meters cubed per day. Okay, second moment. Second moment from point 3 to point 6. What is the value of the rate of change at the start of that moment? Exactly. R sub v of 0.3. What would it look like to have a constant rate of that for that constant rate over that whole moment? We would have a horizontal line right there until 0.6. Okay, we already did the third moment. The fourth moment. What's the rate of change at the start of the fourth moment? This is 0.3, 0.6, R sub v of 0.9. What would it look like to have a constant rate of R sub v of 0.9? Try it again. Oh, blue. Okay, and then we can do, let's do one more, even if you didn't do it. So now we have the fifth moment. What's the rate of change at the start of the fifth moment? R sub v of 1.2. And that would be the constant rate for that whole moment. Okay, so this blue function, so this blue graph is a new function, right? It's a new function, but it's all constant rates. It's like piecemeal, right? It's piecemeal constant rates. And do you see that it's trying to be like the red function? So we call it's like pretending to be the red function, but it's really not. But it's kind of like if we only could deal with constant rates and we needed to kind of simulate this red function, it's kind of like the best we could do. Do you see that? So it's like our pretend rate function. Or we also call it an approximate rate function. So now we want to write that function. Can we write that now symbolically? We want to call that just plain old r, okay? So the blue function now is just going to be plain old r of t. And we want to come up with some notation that represents what we drew. Okay, and this was the end of your homework, the very last question in your homework. Something to do with equation 5.9. Okay, so now it's the other way. Now we're going to create it. Rather than explain one that's already given, we're going to create it. So what is really happening? We said from 0 to 0.3, what is the rate? What is this value of r sub t when t is between 0 and 0.3? What do we say? What is this rate of change right here? R sub v of 0. So it's r sub v of 0 when what? T is between 0 and 0.3. But then when t is between 0.3 and 0.6, we have a different value of the rate. So because the graph is in pieces, our definition is going to be in pieces too. You see this? So to get that to describe that blue function, it's in pieces. So now we gotta write it in pieces too. Okay. So our first piece is when t horizontally is between 0.3, and then that we have the constant rate of rv sub 0. And then between 0.3 and 0.6, what is the value of the function? Nice and loud. Someone said it. R sub v of 0.3, the rate at the beginning of that interval. But in the blue function, it's that same rate for the whole interval. That's what this says. It says it's the constant value for that whole interval. Okay, finish it. So, and then what we do is we put this big like bracket thing like this to show all of those pieces put together give us RT. You finish it, okay? Go, you finish it. You get it? Okay, so good point. So I've got the equals wrong, right? So this should have been equal at 0, but not equal at 0.3. No, where is that 0.3? What's the rate at 0.3? What's the rate at 0.3? Yeah. No, exactly. What's the rate at 0.3 exactly? At 0.3. I had it 0. R sub v of 0. So I want to include it with this line instead. See, so when t is 0.3, I want it to be there. So I had the equals and the non-equals backwards. Does that make sense? According to the way we drew the graph? Okay, now finish it. Because it'll be equal at the beginning, but then when you get to the next moment, now that's when you're going to jump down and have the new rate of change. Okay? So it'll be equal at the beginning. So is the wonderful silence, is that because we're done or we're all writing? They're done? Okay, good. Okay, so from 0.6 to 0.9, the rate is R sub v of? From 0.9 to 1.2, the rate at 0.9. And from 1.2 to 1.5, we want the rate at 1.2. So, look, we're picking off rates, single rates from the changing rate function and making them constant rates over that moment. So where before this was a single rate, there's a single rate of change from all those different rates of change. Now in this function, the blue function, it becomes a constant rate over this whole interval. You see? RV of 0.6, that's just the rate at that moment, 0.6 days. But in the blue function, it's the constant rate for the whole moment, for that whole time period from 0.6 to 0.9 days. Okay, questions on that? Okay, so let's start to talk about now that we have these constant rates, we can start building a preliminary accumulation function. An accumulation function. So let's try doing that down here. Okay, so we're going to line things up here. There's 0.5. One, 1.5. Okay, so what are we talking about here? What do we estimate that rate to be at 0? Say 28. So look, now, at a constant rate of 28 meters cubed per day over a time period of 0.3 days, what can you conclude? Or now we're going to apply constant rate of change to get a little bit of change. So at a constant rate of about 28 over a time period of 0.3 days, what can you conclude in terms of accumulation? Think about it. Work on it. Okay? Go. So at a constant rate of 28 meters cubed per day over a time interval of 0.3 days, what can you conclude about the amount of accumulation that occurs? So a constant rate of 28 meters cubed per day means, somebody new, who can tell me what a constant rate of 28 meters cubed per day means? The broadest definition. Who can tell me? Yeah, tell me.
For any change in days, the change in meters cubed is the constant rate times that change in days. So 28.
Well said. Well said. So again, it's got to start to stick sometime. A constant rate of 28 meters cubed per day means given any change in days, the change in volume of oil spilled out is going to be 28 times that change in days. What is our change in days? Therefore, the change in amount of volume spilled is 28 times 0.3. What is it? What is it? 8.4. How many people came up, before I started talking, how many people came up with the number 8.4? Okay, some, but not enough. Doesn't make sense. 28 meters cubed per day means any change in time will result in a change in volume of 28 times that change in time. Or in other words, 28 dV equals 28, that's our approximate, times dt. And we had a dt of 0.03. And then it was 8, you got 8.4? So let's make this 10 meters cubed, 20, 30, 40. So what does that mean? At 0.5 days, how much has spilled into the ocean? What'd you say? Was it 8.4 meters cubed? That puts us about here at 8.4. And at a constant rate between 0.3, sorry. So here, we're at here, right there. So this is the point on our accumulation function, accumulation of oil spilled, of 0.3, comma, what's that point? 0.3, comma, 8.4, which we got by doing dv equals m times dt. So now, in those first 0.3 days, if we change at a constant rate, what will all the correspondence points look like? What will all the correspondence points look like in those first 0.3 days if it's changing at a constant rate? Like this? So at 0 days, how much oil is spilled out? 0. Okay. We want all the correspondence points now on the accumulation function down here. Right, so if it's a constant rate of change, we know that will give us a linear accumulation function. So all the correspondence points from 0 to 0.3 will form a straight line. Okay, so now, in the second interval from 0.6 to 0.9, we can use constant rate of change to find the change in V. But then we're going to need something else because we have a starting volume, and we're going to have a change, and then we're going to have a final volume. Can you continue the graph? Can you continue the graph? Putting everything we've learned in the last month together now. We've got some starting volume at 0.3. We've got a constant rate of change of R sub V of 0.3, and let's all estimate the same value for that. What should we estimate for that? I heard 21. 21 it is. Our estimate for R sub V of 0.3 is 21. Can you put it all together and draw the next piece of our accumulation graph? Put it all together and draw the next piece of the accumulation graph. Go. Using 21 as the estimate for R sub V of 0.3. Show me the math, show me your sketch. Okay. So the first thing we need to know is, what does a rate of change of 21 meters cubed per day mean? What does a rate of change of 21 meters cubed per day mean? Somebody know? Levi, do you know? Good. You got it. So for any change in days, the change in volume is 21 times that change in days. That's what that rate of change means. So therefore, what change in volume do we have over this moment from 0.3 to 0.6? So this time now we're doing dV equals 21 dt. Or we could use deltas here. So we could use deltas because we're actually talking about whole moments. Okay? But what do you get for this one now? Nice and loud. 6.3. What are the units on that? 6.3 what? Meters cubed per day? Meters cubed. What are the units on my y-axis of this new graph? Meters cubed. This, we're doing accumulation, meters cubed. Okay, so I have a change in volume of 6.3. And at 0.3, what was the total volume or accumulated volume filled out at that point? 8.4. Therefore, at 0.6, new accumulated amount equals old or initial plus the change, right? That's that other important principle. The new accumulated amount at 0.6 will be the starting value, 8.4, plus the change, and you got just shy of halfway here. What about all the correspondence points? So that point is 0.6 and 13.7, 14.7. What about all the correspondence points between our two critical points here? We're gonna get, there's going to be a bunch of points in between for all those times and days in between. It's a line because we're constant rate of change will then guarantee a linear accumulation or amount graph if we have constant rate of change. So what are we doing? We're building the accumulation graph given the rate graph. We're using, but we actually had to fudge, right? We've got to start out by constructing this pretend or approximate rate function to give us a fighting chance, because with a continually changing rate, we got nothing. That red graph, we can't do it unless we have some constant rates to do, so we can actually calculate some changes in V and some values of volume. So as we continue to build this function, is it the true accumulation function for the red graph? Is it the true accumulation function for the red graph? No, it's based on the blue graph, right? So is it overestimating the amount of accumulation or underestimating the amount of accumulation? Is it overestimating the amount of accumulation or underestimating? I think most people are saying over. Why is it overestimating the amount of accumulation?
Because the rate of change graph is generally declining versus the blue is generally horizontal.
Okay, I think you've got the right idea, but that's not the reason why. I think you're thinking the right thing, but you didn't say the right thing. Why is this going to be an overestimate? Yeah. That's because we have such a big moment. No, that's not why.
As the rate of change decreases on the red graph, on the blue graph, the rate of change stays at that high number for 0.3 of a moment instead of going down, and only then decreases.
Right. Our rate of change is higher than the actual rate of change. That's a little different than what you said. See that? Yeah. Our rate of change is always higher than the red, except at the very beginning of each moment. Our rate of change is always a higher rate than the actual moment, or the actual rate of change defined by the red graph. So this accumulation function is gonna overshoot. It's gonna give us too much oil spilled in, compared to what the red rate function does. So now I want you to finish this graph. Get all the key points, finish the accumulation graph. So we're applying everything we learned in the last month. We're applying everything we learned in the last month. So you've got what, three more moments to finish this.
Will we be using the same numbers for the...
Oh, so we have to, so what do we say? Let's all have the same values here. For R sub V of 6, 12? I heard 12. R sub V of 0.9? 5. R sub V of 1.2? 3, I heard. Go. So 12, 5, and 3 are our approximates for those constant rates. Yeah. So, but yeah, something like that's why.
I just want people to like to talk. The ones that we tried are going really well.
Yeah.
There's so many. You have to push in 20 of them into getting out there. And only then are they making an effort. So maybe they need to get a wake-up call that they have to actually follow.
Yeah, no, I think
Because the ones that are trying, even if they get along, like, I help them. Things are great.
Right.
They're just,
right. Yeah, it's just
so, yeah, I think the needs to get used to not writing the function just like
no, like this,
drawing the graph.
stuff like
It's
this,
easy for us to read.
like a new context, a new context.
Nothing new.
What's that?
That's new, but that's not because they're having problem with. They're having problem with old y plus d y is new y.
Okay. So I'm just gonna start doing it and let them keep working. Okay. Okay, so to get the change in volume for the third moment, you used 12, is that right? And so what did you get for the change in V? The change in volume in the third moment was what? 3.6? And then in order to get the next ordered pair, we have to apply this, right? What's our initial volume in the third moment? Okay, so what's our initial volume for the third moment? Yeah, 14.7. And so to get the final value of that moment, we're going to take the initial plus that change that we calculated based on this constant rate of 12. So 14.7 plus change of V is 3.6 gives us, nice and loud.
18.3.
Thank you, 18.3. And that's at 0.9 now? Thanks. And then in that moment, if we're at a constant rate for the whole moment, all the correspondence points will make a line. So that ordered pair is 0.9 and final V, which was the 14.7 plus the change in V that you calculated from the constant rate, 3.6. Thanks. And then do it again. So in the next 0.3, we said it was 5. So did it go up 1.5? Change in V was 1.5, added to the 18.3. Is that 19.8? What's happening to my intervals here? 0.3, 0.6, 0.9. What should have been here? 1.2. And when you add, so we got 18.3 plus, these are all straight lines. So 1.2 and 19.8. Finally, the last moment we said was 3, so the change in volume is 0.9 plus the 19.8, 20.7 at 1.5. The units on all my the first coordinates, the horizontal coordinates, are what? What are the units on all those? Days, right? Days since the leak began. What are all the units on these y coordinates? Meters cubed. We're tracking the accumulation of volume into the water. Okay, does it make sense? Okay, so let's just talk a little bit about. Okay, last chance. I'm going to erase all this I've written on the screen. So last chance to ask a question. So hopefully this is feeling better, like in terms of what do all these things mean that we've been doing in the last month. So we're tying it all together now. Given a rate function, we want to build the accumulation function. We can only do that with constant rates. So we build a pretend rate function, or a constant, or approximate rate function. That's the blue one. It's pretending to be like the red one, but it's made up of constant rates. And with constant rates, we can do the math and get changes in volume and get actual amounts of volume expelled into the ocean. Okay, good stuff. Any last chance? Any questions? Oh, good. I almost erased the whole thing. Go ahead.
So is there any specific reason why we're using the initial value?
Oh, good question. So why choose the initial value as the rate of change? It's convenient, and here's a reason, but I forgot. Do you guys remember what the reason is that we choose the? Do you remember what the reason is we choose the initial value? I just forgot.
Let's imagine that instead of knowing the rate, we have a function that we're kind of moving through it. If we use the beginning, then it's almost like we can use it in a predictive fashion until we decide to look at it again.
Okay, yeah, so we think about the number of days increasing as time goes by, right? So we come to a rate, and we're gonna grab that rate, and we're gonna let it be the constant rate for a while until we decide we're gonna pick the next rate. Does that make sense? So it's kind of, you think about days increasing from left to right, and so we just we get the beginning of a moment, we pick off that rate, and then we just let it be that rate then for the moment. Does that make sense? Yeah. So thinking about the independent quantity increasing from left to right, it kind of makes sense to Go ahead.
Doing the right or doing the middle is wrong, and in fact, we might ask you questions like that in order to see if you really grasp the idea. But this one seems the most like common sensey, so that's the one we're going to go as our standard. So the textbook is going to use the left as your end of convention, so you're going to see that throughout the whole textbook.
Okay, so they're using terms, they use the terms left, right, and middle. So this is, because we use the rate at the beginning of each moment, that's the left side of the moment. So this is what also is called the left approach. Left approach, because we took the rate at the start or at the left side of each moment. So we could have gone here in each moment, and we could have taken the middle. Looked at the middle of the moment, picked off that rate, and made that the constant rate for the whole moment. Or we could have taken the right. So it still works to choose the constant rate a different way, but this is the way that the text chooses. Okay? Can I erase? Last chance. Okay, let's do top hat. Hopefully we got internet now.